All right, we are now recording. Let's get the setup from current slide. We'll pick up and go from there where we left off last time, which I think was on the C part. There's A and B. There's C. Okay. But before we do there, here's just a few announcements. Okay? First, and this comes up right after class, okay? Counseling Services are offering a seminar titled Drug Use and Its Legal Repercussions. This is being presented by Lawson State's Chief of Police, Chief Blanton. He's usually on the Birmingham campus, but he's coming over today to do this seminar. And this is it's a student services seminar today, the 30th, my brother's birthday. Faculty staff dining room, that's in this building, from 11:30 to 12:30. So it's right next to the cafeteria, so if you wanted to grab lunch and go next door. How you get there from here or wherever you are, here's where we are now. Go out in the hallway, go down this long hallway, go past the first stairwell, the second stairwell. You get one of those, there's two pieces. Okay. You go down that first part of the flight, you get onto another level here, go through that door, make a little zig there, and take a left. Faculty staff dining room is there, or over here, okay? 3 entrances here. This is the cafeteria right here. These are all first floor. They didn't show it here, but they showed it there. There's the faculty staff dining room, okay? And you'll be there 11:30 to 12:30. I think you said you had a class right after this. Okay. And you do too, right? Okay. Following me in. Okay. So, Sarah's here. Whoops, wrong pen. Okay. So that's today from 11:30 to 12:30. Okay. Now, if you need more information, you can contact Dr. Renee Herndon. I have a phone number and email address for him. Ms. Kimberly Moore, phone mail and email address for her. Later today, he's going to be on the Birmingham campus doing the same seminar. So if you happen to be going over there this afternoon, from 1 to 2, he'll be doing the same in the Leon Kennedy Center. That's the student center. The cafeteria is downstairs. Go upstairs to room 207. It's the Space Center, and that's from 1 to 2 today. Now over there, contact Ms. Janine Jones. I've got a phone number and email address, and also Ms. Leslie Harper. I have a phone number and email for her as well. I was just relaying that there's going to be 2 counseling services seminars today, drug abuse and legal repercussions, presented by Chief Blanton, the chief of our police department, here on this campus in the faculty staff dining room between 11:30 and 12:30 on the Birmingham campus this afternoon in the Leon Kennedy Center, 2nd floor, Space Center 207 from 1 to 2. That's today. Now, lunchroom today, I'll give you Bessemer first, and you can look at Birmingham if you're interested. The Bessemer, all they have is TBA for today. That's good old TBA, delicious stuff, But tomorrow is taco salad, and I'll give you the rest of these later. If you are interested in Birmingham, they have both the noon meal and the evening meal, if you're interested in that. And please, folks, if any of you are interested, if you'll be here in the fall, interested in participating in the math team, Mr. Rossi on the Birmingham campus will be having practice sessions. I think they've decided on Monday, Wednesday afternoons at 3, and maybe not every Monday and Wednesday, but some afternoon at 3. They had tried Fridays at noon, but that didn't work for some of the students, so they are going to try the other. I can have it anytime here if you want to have some practice sessions here, anytime during my office hours. So I'll be glad to. They're fun things to do. Okay, one more announcement. This pertains to this class. Okay. I think I told you early in the term that I have a mild form of leukemia. And so I go in for treatments, usually have been going once a month. Well, they have me on what they call a monoclonal antibody, and that's become less effective. Not doing as good a job keeping the counts down. So the doctor, I saw him that Tuesday. We had the weather day on the 16th, and he wanted to try a different drug. So as a newer one, he's had some really good results with primary, situations with it. Mine's a recurrent type thing, so he thinks it may work. They got approval to try it, and the insurance don't cover what they do on it. We got a big copay. But the first treatment, they have to check and see. Monoclonal antibodies are developed in animals, usually rats, I think, as they come up with them. So, and then they try to strip off all the things that, residue that have any rat quality to them, just have the antibodies. Well, they're never 100% effective. So there is a chance your body's going to try to reject something. And so they give you steroids, they give you Tylenol, they give you Benadryl, and all sorts of things to keep down the reactions. And because this is a new one, I haven't done it before, the Thursday, we got a phone call yesterday, or phone message yesterday when we got home from work, that they want me to come in for the treatment Thursday, day after tomorrow, okay? And the first treatment, it's usually going to be on Fridays, but this first time they do 10% on Thursday, see how you handle it, and then do 90% on Friday. So I've got to miss all day Thursday. And they say it will be all day because they do it really slowly and make sure you don't have any negative reactions. So I'll be in there for blood work at 6:30, start infusion at 7, and basically go all day long. So we will not have class on Thursday, okay? And I'm not available to have it on Friday because I'll be having my 90% on Friday. So we will have class next Tuesday at 9:30. If you want to try to schedule this one to follow up sometime later, either Monday, Tuesday, Wednesday, or Thursday, but I can't do next Friday because it's going to be every Friday for a month, and then they'll go once a month. So is there one day or other better or worse for you, Monday, Wednesday, or Tuesday, Thursday?
I have a 9:30 class. Okay, I can do it in the afternoons.
On Tuesday, Thursday, or Monday?
Any day.
Any day. How about the rest of you?
Yeah, we have the same classes.
Okay.
At 3 every day.
And what?
It's at 3 every day.
At 3. You have a class at 3?
We get done at 3.
Oh, you get out at 3. Okay. And how about you? Are you free after 3 any day next week?
No. I have class in the Birmingham classes around that time.
Oh, okay. All 4 days? Monday through Thursday?
No, I can do Monday.
Monday?
Yeah.
Okay, now, I've got class in here until 3:15 on Monday, but after 3:15 I'm free. So you want to do it, say 3:30 on Monday? 3:30 to 4:45? Okay, so we won't have class. Huh?
No, I meant Tuesday.
Tuesday.
Yeah.
Okay, Tuesday, 3:30.
Yes.
Okay, yeah, I'm free then too. Okay, because I'm going to make up my 112 class at 12:30 to 1:45, and then we'll do this one 3:30 to 4:45. And here till 5:15 anyway.
My
So.
class on Tuesday is at Birmingham and it gets done at 3:15. So
Oh, it
I'm
does?
a couple minutes late.
Okay, that will be fine. Both of you? Okay. You want to make it 4?
I'm good with
Huh?
I'm good with that. And
Which?
either way. I'm good at 4.
At 4?
Yeah.
4 okay with you on Tuesday now, right?
Yeah, I can.
You do like 3:45, like halfway in the middle.
Say again?
Like 345?
Oh, wait. Yeah, oh, I'm sorry, we didn't have to jump that far, did we? Yeah, 3:45 will be fine. 3:45 till 5 then. Will that work okay?
Yeah, I can wait that.
I'm sorry?
Zach will wait that long.
Okay, you can make that. So that'll be Tuesday then. All right. So we'll have class Tuesday morning at 9:30 and then again at 3:45 in the afternoon to make up Thursday's class. So Thursday, 3-day. Okay. For me, I mean, you have other classes. All right. All right. Good deal. And we'll talk about it again on Tuesday. Okay. So where we left off last time was, I'll back up one. Okay. We had done on page 274, example 2, this is in 4.2, we had done the A and B part, and that's the last part of B right there. The C part says for, whoops, let me get my pen set up. Sine of t equal 4/5. What is the sine of negative t? If sine of t is 4/5, what is sine of negative t? Anybody? Anybody? This is on page 274, top of the page. Example 2C. Where would you begin? What would you do? Just a little hint. Anytime you talk about a function, any function, you're talking about at one value or the opposite of that value, the thing that should come to mind is even and oddness. Is this either an even function, an odd function, or a neither function? If it's a neither function, usually you can't say much about it. If it's an even or odd function, yes, you can say something about it. So this is sine of t equal 4/5. Now it's asking what sine of minus t would be. Is sine either even, odd, or neither? It's an odd function. So that what would that make sine of negative t to be? Negative 4/5, the opposite of that. Because if it's going up over here, sine of t is 4/5. Sine of minus 4t is going to be minus 4/5. You're absolutely right. Minus 4/5. What if that had been a cosine here? Cosine t 4/5, what would have been cosine of minus t? That would have been cosine t is equal to 4/5. What would have been cosine of minus t? Okay. The best way for me is to think about how the graph is. Okay? So when I think of a sine, I always think of this. Sine goes like this. Okay? So whatever you go in here, you do the opposite there. See, it goes up here, down there. That's odd. That's an odd function. Cosine, on the other hand, looks just like a sine, except it starts at 1 and does this. Well, it goes a little bit further. And so whatever it does here, the value is the same here. That's even function. It's even across here, This is odd because it's opposite across there. Okay?
So if it was cosine of -2, would be just 4/5?
It would still be 4/5. Cosine of -t would still be positive 4/5 because it's the same on either side. Okay. Tangent would have been tangent is pi. Okay, so it would have been minus 4/5 if tangent would have been 4/5. Cotangent. It's odd too because it's reciprocal of tangent. So that's going to be odd. Secant. Now, number one, secant will never be 4/5. We haven't talked about that yet, but it just never will. Secant is always greater than 1, greater than or equal 1, or less than or equal to -1. So it can't ever be 4/5. So let's say 5/4. If secant was 5/4, what would secant of minus t be? It's also 5/4 because it's the reciprocal of cosine, and cosine's even, secant's even. How about cosecant? Again, it would have to be 5/4, not 4/5. Negative 5/4. 5/4 because it's reciprocal of sine. Perfect. Very good. Any questions on that? Okay. Let me clear my chicken scratch out of the way, and let's see how they do it. And it says for sine of t equal 4/5, sine of -t has to be negative 4/5. Not much of an exercise. They just give you the answer because the sine function is an odd function. Okay? Now, when you're evaluating trigonometric function with a calculator, you need to set the calculator to the desired mode of measurement. In other words, either degree or radian. If you're in radian mode and plug in a degree, the odds are you're going to get a really wacko answer. Okay? And vice versa. If you're in degree mode and plug in a radian, you're going to get a totally wrong answer. Okay? Except for very few places, like 0. That would be the same in both. Most calculators do not have keys for cosecant, secant, and tangent. All they have keys for is sine, cosine, and tangent. But since we know that the cosecant is the reciprocal of sine, secant is reciprocal of cosine, and cotangent is reciprocal of tangent, then we can do the x to the -1 key on some calculators. Other calculators is 1/x key is the reciprocal key with their respective reciprocal functions, sine, cosine, and tangent. Okay? So let's see what that blah, blah, blah is talking about. So here's one. To evaluate the cosecant of pi/8, okay? Look on your calculator. You'll never find the cosecant key, I don't think. Maybe not even the really big, expensive, fancy calculators. Maybe there are some that have them. Most of the time they don't. So if you don't have a cosecant key, how are you going to do this? Well, you know that cosecant of pi/8 is 1 over the sine of pi/8, and you can do that on any calculator. Not a cheapie, a freebie, but any scientific calculator or better, you can do sine of pi/8. So there's two ways you can do it. If you see cosecant of pi/8, you can do 1 over, or 1 divided by, sine of pi/8 equal, you'll get the answer. What they suggest, oh, and by the way, what mode are you in when you see pi/8? Radian. You have to have that little degree symbol before you be in degree. If you don't see the degree symbol, you're in radian mode. So make sure you're in radian mode, okay, first, and then you can either do 1 divided by sine. When you do the sine key, it's going to usually open parentheses, pi divided by 8, close parentheses, equal. That will give it to you. The way they suggest doing it, and it's no better or worse, is fewer keystrokes perhaps. Open a parentheses here, okay? The reason is you're doing this whole entity here, okay? open parentheses, sign. When you press the sign key, it opens the parentheses already. Then do the pi key divided by 8, close this parentheses, then close the first parentheses, then press the x to the minus 1 or the 1 over x key and press enter. I'm not even sure you'll always have to press enter. I think when you do 1 over x or x to the minus 1 key, it may give you the display like that. And here's what you get, 2.61, blah, blah, blah. Now, is that a reasonable answer for cosecant? Cosecants can never be between minus 1 and plus 1. Ever. So anything outside of greater than 1 or less than minus 1, perfectly fine. That's a good answer. If you got this answer for a sine, you're wrong. Okay, because sines are always between minus 1 and 1. And cosines are. Tangents and cotangents can be anywhere. Okay? Secant and cosecants are outside of plus or minus 1. Greater than plus 1, less than minus 1. Less than or equal to. Okay? So yes, that is a perfectly legitimate answer. Did you try it on your calculator? Because it's a good idea to know how to use them. You can either use that key or, like I said, do 1 divided by sine of pi 8. That works just as well. And actually, by the time you put all those parentheses in, it's probably as short to do 1 divided by. Everybody get it? Or have you got your calculator? Okay. If you're comfortable with that, let's try these two. I hate it. They give you the whole thing. All right. Sine of 2/3 pi. What's the first thing you check for? What mode are you in? What mode are you in? Radian, because there's no degree symbol. Okay? And so once you're in the right mode, then you just press the keys as you're in. Sine, and when you press the sine key, you open, most calculators already open that parentheses for you. Then you do 2 pi. Now some of the older calculators you have to do 2 times pi. Most of the newer ones you can just do 2 pi. There's a pi key somewhere on your calculator if you have a scientific or better. Okay? And then divided by 3, close that parentheses, press enter, you got it. Is that a reasonable answer? Yes, it's between minus 1 and plus 1. It's also reasonable, and where in the world are you all done at 2/3 pi? Second quadrant, sine is positive, so also you take that calculus. Okay, yeah. Sine is positive there. Yeah, I feel very good about that. And they're right. Yeah. Okay, how about this one? Cotangent of 1.5. Calculator have a cotangent key? I thought not. Okay, and 1.5, what mode are you in? Second? Radian, because if they had a degree symbol, you'd be in degree mode. You do not, so you have to stay in radian mode. And since you don't have a cotangent key, what do you use? Okay, yes, the reciprocal key, or just 1 over. Frankly, I would say 1 over tangent of 1.5. Just as easy to do. 1 divided by c, the tan, and it opens the parentheses, 1.5, you're in radian mode, close parentheses, hit enter again. Or you can use the reciprocal key, and in that, when you open with the parentheses, tangent of 1.5, close that, then hit the reciprocal. Now, you might ask yourself, why do you need that opening and closing parentheses? Why couldn't you just do tan? It opens the parentheses, 1.5, and then press the x to the minus 1 key. And then the enter. What do you say? It takes the reciprocal of the 1.5, not the tangent. So you want it to take it of the tangent, so that's why you have to put parentheses here and here. That's why you have a double set. That's why, to avoid that error, you do 1 over tangent it's taken care of. You don't have to worry about that. So either way works. Is 0.709 a reasonable answer? Tangent can have any all real numbers in its range, so yeah, that doesn't tell you anything. But 1.5, where is that? Ooh, where are you, Waldo? Well, 1.5 radians is a kind of a tough one because this is 0 radians. That's pi radians. How much is pi? 3.14. So exactly half of pi would be pi halves, but half of 3.151416 would be 1.57. So yeah, you are just short of pi halves. Okay? Now, tangent of pi halves is going to infinity. Really close. But you're not there yet, so you can do that. 1.57, go be here. So yeah, pi halves you couldn't do. So this is getting close to that. So that's a huge number, but 1 over that is going to be a very small number, but positive. So yeah, that makes sense. Good deal. All right, and by the way, every one of these examples has a checkpoint, so please check on the checkpoints. And they have audio video solutions at larsonprecalculus.com. So as soon as you can after class, if you can go do those checkpoints while they're fresh on your mind, it's a good way to get on top of this stuff. Well, that finishes 4.2. Let's do the vocabulary of 4.2. Each real number t corresponds to a point xy on the blank blank. Second? It certainly does, but what we're talking about with trig. Unit circle, very good, okay? Number 2, a function f is blank when there exists a positive real number c such that f of t plus c is the same as f of t for all t in the domain of f. A lot of blah, blah, blahs, huh? Okay. A function f is blank when there exists some positive real number c such that f of t plus c is the same as f of t for every t in the domain of f. In other words, if you go along here to t and then do a t plus c, you're guaranteed to be at the same place each time. Another c, you'll be at the same place. Another c, you're at the same place. In other words, and that's true for every t. It's up here, see you later, you're going to be up here again. See you later, you're going to be up here. It's down here, see you later, you'll be down here. See you later, you'll be down here. In other words, this function repeats itself each period. So it's a periodic function. That's your definition of a periodic function. Okay? That's number 3. Number 4, a function f is blank when f of minus t is equal to minus f of t. Odd, okay, and blank when f of minus t is equal to f of t. Even, very good. And if not either one of them, it's a neither function. But all your trig functions are either even or odd. Okay. Polynomial function, not. Okay. Always. Okay, homework exercises here. Do either 5 or 7 or both. Either 9 or 11 or both. And by the way, all odd number exercises have answers in the back, plus they're at calcchat.com if you can't get the answers that are in the back. Then do any of the odds 13 to 21, and then do any of the odds 23 to 29. All the odds, again, are at CalcChat, but number 23 is also at CalcView. And there's a little, what I call square barcode there that you can click with your phone if you have the app in there, and you can pull it up directly. Then do any of the odds 31 to 35. All of those are at CalcChat. 31's at CalcView. Do any of the odds 37 to 41. All of those are at Calc Chat, but 37 is at Calc View. Do any of the odds 43 through 47. Okay? Then do some of the, well, no, there's only one. Do 49. That's a harmonic motion problem that is a periodic function dealing with the periodicity. And then there's some true false. A couple of those answers I think are in the back, and they should be at calcchat.com. Don't sweat too much about them, but understand why they're true or false. That's the main thing. You're not going to get true false on a test. Okay. There's a conjecture in 55. You can look at that if you like. Error analysis in 57 if you're interested. And a technology problem in 59 if you have the technology to do it. Graphing utility. There is a think about it in 61. Well worth your thought, but I wouldn't spend too much extra time on it. Okay. All right. That finishes 4.2. Any questions on 4.2? Okay, let's get out of 4.2 and move to 4.3. Sorry, my head's clogging up on me. Now, 4.2 dealt mostly with the good old unit circle. 4.3, which we're starting now, let me get the slideshow set up for the current slide. Chapter 4 is still trigonometry, measurement of triangles. We're finally going to get to triangles, okay? We've been in circles so far, running around the unit circles and not getting anywhere. Now we're going to do right triangle trigonometry, which to me is how I first learned it and then applied it to the unit circle. Most new books do the unit circle first and then apply it to right triangles. Okay? What we're going to do, our objectives here, evaluate the trigonometric functions of acute angle, part of A, less than 90 degrees or pi halves, radius, and we'll use a calculator to evaluate trigonometric functions. We just did some of that. You will use fundamental trigonometric identities. We've hit those a little bit. We're going to hit them again. And we'll use trigonometric functions to model and solve some real-life problems where the rubber meets the proverbial road. So let's start with the 6 trigonometric functions. But now we're not defining them on a circle anymore. We're defining them with triangles. Okay? So this section introduces the trigonometric functions from a right triangle perspective. Now what do we mean by right triangle? It has one angle that's a 90-degree angle, or a pi-halves angle. Okay? That's what the little box here stands for. That means it's a right angle. I think I told you why we say it right angle. Because the Greeks believed it was the perfect angle. It's where you get the maximum strength of a building. That's why you don't have buildings with walls that lean out and stuff like that. Not very good strength. The weight tends to pull them down either way. So a right angle, that's going to be your strong angle, the right angle. Okay? So one of the 3 angles in that triangle is a right angle. Can more than one be a right angle? No, why not? The sum of the 3 has to be 180, and if 2 are 90, you're already at 180, you can't have another angle. That would be a triangle, then, would it? Okay. So, you'll have a right angle on one, the other 2 are guaranteed to be what kind of angles? Acute angles, because they have to be less than 90, because the sum of the 3 is 180. If that's 90, the sum of these 2 is 90, and what does that make those 2 angles? Wow, your hair is pretty today. Complementary angles. Oh, very good. Okay. All right. So we'll consider a right triangle with one acute angle labeled as theta. That's their favorite name for an angle, by the way, is theta. Just like x is a favorite name for a variable. Okay? You can name them other things, but they love theta. Relative to the angle theta, the three sides of the triangle are then always the side opposite the 90-degree angle, or the pi-hash angle, is the hypotenuse. Always. Now, here's something about any triangle. Any triangle. The side opposite the largest angle is always the longest side. The side opposite the smallest angle is always the shortest side. The side opposite the middle angle is the middle side, okay? So the hypotenuse, because this has to be the largest angle, it's 90 degrees, these two add to 90, so they've got to be less than 90, acute, so therefore the hypotenuse is always the largest. Okay? Now, relative to this angle theta, that's the side opposite theta, the one over here that does not touch theta at all. Hypotenuse touches theta, and the adjacent side touches theta. The opposite side does not touch theta at all. Okay? It's the opposite side. This is the side adjacent to theta, or the adjacent side. Now, using those lengths of those three sides, we can now form the 6 ratios. Remember, your trig functions are ratios. And these define the 6 trig functions of that acute angle theta. Okay? Here are the 6 functions. Sine, cosine, tangent, cotangent, secant, and cosecant. That's the order I like them. They always list them this way, which is bizarre to me. And this abbreviates as SIN, COS, SEC, southeast circumference. TAN, COT, this one. You can't do COS because you already use COS. So you use the first 3 consonants, CSC. That's cosecant. Okay? What are those ratios? Here they are. Now remember your triangle. Opposite side, adjacent side, hypotenuse. Okay? So any angle that's an acute angle between 0 and 90 lies in the first quadrant, and these have the meaning. That theta be the acute angle of a right triangle. The 6 trigonometric functions of that angle theta are defined as follows. Note that the functions in the second row are reciprocals of the one in the first row. Okay? So the sine of theta is always the ratio of the opposite side to the hypotenuse. Cosine is the adjacent side to the hypotenuse. Tangent is opposite side to adjacent side. Cotangent is adjacent side to opposite side. Secant is hypotenuse to adjacent, and cosecant is hypotenuse to opposite. Those are your ratios. So these abbreviations, OPP for opposite, ADJ for adjacent, adjective, and HYP for hypotenuse. Now, most of the time I won't even use 3 letters. I use O, A, and H. Okay? Now, the very first term I think that I taught trig here, back then we were at Western State Technical College, and a gal who sat right back there in that seat was in this classroom. When I went over these the first time, she said this. I'd never heard it before, but it's sort of cute. Some old hen caught another hen taking, she said it. Some old hag caught another hag taking oats away. Here's what she meant. Some old hag caught another hag taking oats away. That the sine is opposite of her hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over cosine. Now, a few terms later, I was teaching trig again, and I think I mentioned that one, and this other gal said, oh, I heard it as some old hen caught another hen taking oats away. I like hens better than hags, so that's the one I use. Now, my roommate in college, I was in grad school at Nebraska, and he was an undergrad, and he was taking trig because he was going to be an actuarial science major, and he needed calculus for that. And he And I've seen other people use it too. In fact, the book may mention it. They say Soh, S-O-H, Ha, C-A-H, T-O-A, Toa. Sakatoa. Sort of like Sakatumi in the old days, but it's Sakatoa. But I had trouble with that because the Sa and Ka, which is O and which is A, you know, I had to remember. Of course, I learned it as sign is opposite over hypotenuse because that's how I remember it, and then I tell students these other things, okay? So that's another way, Sakatoa. If you can remember the S is the O and the C is the A, Toa is easy, okay? If you got those, you got them because the others of this are reciprocal. The tangent is reciprocal of this. I mean, cotangent is reciprocal of tangent, secant is reciprocal of cosine, and cosecant is reciprocal of sine. And if you recall, I mentioned this to you when we were doing unit circle. The thing with the unit circle, the hypotenuse is always 1. So this is the opposite side, which is y. This is the adjacent side, which is x. And this is opposite over adjacent, is just like y over x. X over y. 1 over x and 1 over y. Same thing. Why do they make a big deal about it? It's the same definitions. If you use opposites adjacent, so hypotenuse, it always works whether the hypotenuse is 1 or not. Okay? Pretty straightforward. Get to know them. Okay? That's one thing to remember. Sakatoa, some old hen, whatever you need to do. Okay. So let's do example 1. Use the triangle in this figure, and this, by the way, is on page 278, top of the page. In this figure, to find the 6 values of the 6 trigonometric functions of theta. Well, let's name those 6 to begin with, just so we'll get them down pat. What are they? Sine of theta. We'll come back and figure out what they are. Next, cosine theta, tangent theta, cotangent theta, secant theta, and cosecant theta. Okay, now what is the sine of theta? Yes, opposite over hypotenuse. And what is the opposite in this problem? 4. But we don't know the hypotenuse, so we can't do it, can we? I got to sneeze on that. Not crying, but, you know, I was trying to. Sorry. I will wake you up. Okay. Do we know the hypotenuse? How can we get it? Second? Oh, you're absolutely right. Right off the top, that's a 3, 4, 5 triangle. Okay? You weren't supposed to necessarily know that, but it's neat to know. How do you get it if you didn't know that? Pythagorean theorem. 3 squared plus 4 squared equals hypotenuse squared. 3 squared is 9, plus 4 squared is 9 plus 16 is 25. Square root of 25 is 5. You got it. So we do know what it is. So what is the sine of that angle theta? Four over 5. The cosine? 3 over 5. Tangent? 3, exactly. Which, by the way, writing them this way, just put sine over cosine, which is tangent, by the way. The 5's go out, and you get 4 over 3. See how that works? What is cotangent of theta? 3 over 4. Perfect. And secant of theta is 5 over 3, and cosecant of theta is 5 over 4. Boy, I wish I could make it harder, but I haven't figured out any way to do that. Okay? There you have it. Does that make sense? Get to know those relationships. Like your best friends, you know. They will be. All right. I hope I can make it. Can't breathe right now. Okay. I'm going to clear my scratch if y'all are okay with it. Okay. And we'll see how they did it. By Pythagorean theorem, that's how they started, that the hypotenuse squared is the opposite square plus adjacent squared. In other words, the hypotenuse is the square root of the opposite square plus adjacent squared. And by the way, it's always the principal square root. Why? Hypotenuse is always positive. If you go around the unit circle, we're not doing that yet, not unit circle, around the coordinate plane. Right now we're only in the first quadrant, everything's positive. But when you start going around it, then you're over in the second quadrant, your adjacent side is negative, your opposite side is positive. Hypotenuse is always positive. Go to the third quadrant, your adjacent side is negative, your opposite side is negative, your hypotenuse is always positive. Go to the fourth quadrant, your adjacent side is positive, your opposite side is negative, and the hypotenuse is always positive. So that's always a positive, the principal square root. 4 squared plus 3 squared, that would be 16 plus 9, which is square root of 25, which is, of course, 5. Positive 5. Always positive. Hypotenuse is always positive. Okay? So therefore, the 6 trigonometric functions are sine is opposite over hypotenuse, some old hen, and that's 4 over 5. The cosine is called another hen, that's 3 over 5. Tangent is taking oats away, and that would be 4 over 3. And the cotangent, well, they're going to do cosecant, knowing them. Yeah, cosecant theta would then be the reciprocal of sine, which is hypotenuse over opposite, which is 5 over 4. Secant is reciprocal of cosine, which is hypotenuse over adjacent, which is 5 over 3. And then the cotangent of theta is always the reciprocal of tangent, which is adjacent over hypotenuse, which is 3/4. Good deal. Pretty easy, right? All right, that was example 1. Okay, in example 1, you are given the lengths of 2 sides of the right triangle, but not the angle theta. Often you'll be asked to find the trigonometric functions of a given acute angle theta. To do this, you construct a right triangle, having theta as one of its angles. Now, remember the angles we knew and loved, okay? 0, of course, is pretty easy, and pi half is pretty easy, 90 degrees. The others we like a lot are 30, 45, and 60. Or pi 6, pi fourths, and pi thirds. Okay? So sine of 30, if you remember back from unit circle days, same function, same thing. The sine of 30 degrees is the same as sine of pi 6, so pi 6 radius is 30 degrees, and that was the opposite side was your short side, because that was a small angle, and that was half the length of the hypotenuse. Okay? So that was 1/2. Okay? In fact, I like to think of these in terms of 2 unit circles. Not unit circles, 2 circles. Okay, where the hypotenuse is 2, because the hypotenuse is in the denominator of all the sines and the cosines. Okay? So since it's there anyway, make it a 2 circle, and then 1's going to be your short side, and square root of 3 is going to be your long side. And it will work. Okay? So sine of 45 is sine of pi fourths, those are the same. And that's square root of 2 over 2. Remember, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2. Square root of 4 over 2 would be pi half. Okay? Cosine goes the other way. Cosine of 30 is your square root of 3 over 2. Cosine of 45, or pi fourths, is the same, square root of 2 over 2. Cosine of 60 degrees is the same as sine of 30 degrees, which is 1/2. And then going to your tangents is the ratio of sine over cosine. 1 over root 3, which is root 3 over 3. This one This over this, same thing. This is 1. Tangent 45, tangent 5/4. And tangent of 60 would be root 3 over 1. The 2's cancel out, and it's root 3. Same as they were before, so get to know these are your handy dandy, very useful ones. If you got these, you got all 6 of them pretty much in it. They didn't show the reciprocal ones, but that would just be the cotangent be reciprocal of tangent, secant reciprocal of cosine, and cosecant reciprocal of sine. Okay. Now, what I pointed out is also true. Notice that the sine of 30 is equal to the cosine of 60. They're both equal to 1/2. That occurs because 30 and 60 are complementary angles. Okay? And have you ever wondered why the cos were in there? The sine of an angle is the same as the complementary sine of the complementary angle. Cosine of the complementary angle. Those are the same. That CO, actually, they stand for cofunctions, okay, of the complementary angles. It can be shown from right triangle definitions that the cofunctions of complementary angles are equal because the hypotenuse is the same. And what's the adjacent of this one is the opposite of that. The adjacent of this is the opposite of that, and the opposite of this one is the adjacent of. So opposite of that is the adjacent of this one. So the ratios are, and the hypotenuse is always the same. The ratios will be the same. Okay, so it can be shown that the definition of the cofunction of complementary angles are equal. That is, if theta is an acute angle, then the following relationship is true. Sine of 90 minus theta is always going to be an acute angle, and that will be the cosine of the complement of, well, the sine of the complement of theta is the cosine of theta. The cosine of the complement of theta is the sine of theta. The tangent of the complement of theta is the cotangent of theta. The cotangent of the complement of theta is the tangent of theta. The secant of the complement of theta is the cosecant of theta, and the cosecant of the complement of theta is the secant. The function and its cofunction have the same values for the other complementary angles. And of course, pi fourths is pi fourths, so those are the same for, pi fourths and pi fourths are complementary angles, so those will be the same. I think that maybe they're skipping a few exercises, aren't they? Like example 2. And by the way, the book has these, not often, but they do have them every now and then. Here's a historical note. Georg Joachim Radicus, way back in the 1500s, was the leading Teutonic mathematical astronomer of the 16th century. He was the first to define the trig functions as ratios of the sides of right triangles. Okay? Radicus, you don't hear him talked about too much. Way back in the Greek time, you hear him talk about Aristarchus, who came up with the first set of tables, but Radicus defined them as ratios. So let's do example 2. Let's see if I can find some white space. All right. This will be the best I can come up with, I think. Find the values of sine of 45, cosine of 45, and tangent of 45. Well, let's first draw that being the right angle. And let's assume those two lengths are the same. So that side, so this is 45 degrees, and that's 45 degrees. Okay? Now, when we were dealing with unit circle, your hypotenuse was the thing that was always 1, right? Now that we're dealing with triangles, you can set anything equal to 1 you want to. Okay? And to me, it's far better to call each of these two sides 1. Right? Because they've got to be equal sides, because that's 45, the equal angles, so the opposite sides have to be equal too. So let's just name them 1 and 1. What does that make the hypotenuse? Does the name Pythagoras ring the bell? What's that? Square root of 2, absolutely. Because 1 squared plus 1 squared is 1 plus 1 is 2. Oh, high-level math today, okay? And that's the square of the hypotenuse, so the hypotenuse has to be square root of 2. Okay? And then from that, you can write down, they only ask for 3, we'll do all of them. What's the sine of 45 degrees? A little louder. Square root of 2. And if you don't like having the radical in the denominator, that becomes 2. Perfect. And that's what we remember from before. What's the cosine of 45 degrees? One over root 2 again, which again would be root 2 over 2. And the tangent of 45 degrees? 1 over 1, which is 1. Yes, 1. Okay. Cotangent of 45 degrees. Cotangent of 45 degrees would be, say again, 1. Secant of 45 degrees. Square root of 2. Don't go to this one, go to that one. Reciprocate it to square root of 2. And the cosecant of 45 degrees is root 2 also. Perfect, perfect, perfect. That was a little bit extra, but no extra charge for it. Okay. Oh, that was a checkpoint. Look at me. I just did the checkpoint for you. But you'll say you can do them, but we just did them. All right. Example 3. Can I go on and erase? Okay. I just cheated you out of your checkpoint. Sorry about that. Okay, evaluating the trigonometric functions of 30 and 60 degrees. All right. And it's something very similar to what we did before, only this time we get to draw anywhere we want to. So let's draw it like this. Ooh, I can't draw straight lines very well. And they probably aren't very accurate. But this is going to be an equilateral triangle, the outside triangle. So these 3 sides are the same. This is going to be the bisecting line of that one, making a right angle on either side. And since that splits that absolute, oh, and equilateral triangles are all 3 equal sides, which means, what about their angles? They're all equal, and if the 3 sides of and 3 angles of a triangle are equal, what do they all have to sum up to? 180, so 3 times theta, maybe, is equal to 180. What would theta be? 60. So each one of these angles here is a 60-degree angle. And if you split this one in 2, that makes it a 30-30, because it has to add to be 60. Okay, now we got a 30, 60, 90 triangle. Now the shortest side up there, the very shortest side up there, is this one of these 2 here. So let's just name those 1s. Okay, we get to choose what length they are. Okay, now what does the base of that triangle then be? What is that length? 2. If it's equilateral, that means these 2 sides are 2. So this is a 2, and that's a 2. All we have left to do is figure out what that side is. How do we do that? And how does that work? The square root of 3. You got it. Because the hypotenuse squared, 2 squared is 4, minus the adjacent side, if we're using that adjacent 1. 4 minus 1 is 3. Square root of that is square root of 3. Perfect. And now you can write down every one of these. Let's start with, you want to start with 60s or 30s? I don't care. 30s, okay? What's the sine of 30 degrees? One over 2. Cosine of 30 degrees. Square root of 3 over 2. Tangent of 30 degrees. One over root 3, and if you wanted to rationalize that, that would be square root of 3 over 3. Cotangent of root 3, cotangent of 30 degrees. Root 3, perfect. Secant of 30 degrees. I can't say it right for some reason. It's 2 over root 3, and if you wanted to rationalize that, that would be 2 root 3 over 3. Pretty good. My writing stinks, but otherwise it's fine. How about cosecant of 30 degrees? 2. Okay, perfect. Okay. How about 60? Sine of 60 degrees? Whoa. What's that? Root 3 over 2. Cosine of 60 degrees? One over 2. Perfect. And tangent of 60 degrees? Root 3, is that what you said? Yep. Cotangent of 60 degrees? Root 3 over 3. Or 1 over root 3. Either one will do. Secant of root 3. Secant of 60 degrees. I can't say it right today. What would that be? 2. Okay. And cosecant of 60 degrees. 2 root 3 over 3. Perfect. Okay. Now, things to note here. What color do you want me to do my connecting lines? Red, okay. Let's see if I can get red to come up. There we go. Notice that sine of 30 is exactly the same as cosine of 60. The cofunction of a complementary angle is the same as the function of the angle. And cosine of 30 is the same as sine of 60. And tangent of 30 is the same as cotangent of 60. And cotangent of 30 is the same as the tangent of 60. And the secant of 30 is the same as the cosecant of 60. And cosecant of 30 is the same as the secant. So the cofunctions of complementary angles are equal. Okay. Okay. Now, I think I already hit this table, so I've sort of got out of order there. Let's use a calculator. Here, finally, after section 1, when they gave you exercises in it, now they give you something to do with them, with degrees, minutes, and seconds. It says, use a calculator to evaluate secant of, and they don't have this on the slide, I'm pretty sure. No. Let's clear this out of the way. Okay, too? Okay. Okay. Let me get my dark pen back. Oh, man. Use a calculator to evaluate the secant of 5 degrees, 40 minutes, and 12 seconds. Okay. Well, there's a few things you got to do, because there are several. What's that? Over. I can't hear.
The degree, minute, second to decimals.
To decimals, exactly. How do we do that? Okay. So this is going to be the same as the secant, if I could write, of 5 degrees plus 40 over 60, because 40 minutes is the same as 60 minutes is the same as 1 degree, so 40 minutes would be 40/60ths of a degree, or 2/3 of a degree. So that now becomes a degree, plus 12 over what? $3,600. Okay, and that comes from 12 over 60, and that's over 60, and 60 times 60 is 3,600. And that will be now in degrees also, very small number of degrees. So that's what your argument is. Okay, now you can take that and punch it in the calculator and save having to do all the other thinking through it, but you still can't do a secant on your calculator. What are you going to have to do? Yeah, of what? Of what? Cosine, exactly, because it's reciprocal cosine. And frankly, I do it this way. It's 1 over the cosine of whatever that is. 5 point I'm going to write it plus 2/3 plus 1 over 300. I think I'm right there, yeah. 12 will go into 36, yeah. So if you got a calculator, go on and do that. You can do it in one fell swoop if you want. 1 divided by cosine opens it up, and do 5 plus 2/3 plus 5, 1 over 300. Close it equal as you can get it. Okay, what did you say? I couldn't hear you. I wish I had a calculator. I would do it with you, but I don't have one up there. Now, first, what mode are you in?
Degrees.
Ah,
Over degrees.
these are degrees, yeah. give you wrong answers every time.
Yeah.
You got it? Okay. It's a 1.0049. Okay. Not much. Yeah, secants. Let me write down the answer. Approximately equal to 1.004966. You don't need that many digits, but I'm just doing it because the book had them. Okay. This is a very small angle, just barely more than 0. The cosine of a very small angle is very close to 1. So therefore the secant is going to be very close to 1 because it's reciprocal. Whereas a cosine can't be greater than 1, secant's got to be greater. Either equal to 1 or greater. Just like that. Right. So that makes sense. All right. There is a checkpoint here to evaluate the cosecant at a very different angle. All right. Now we're ready for some trig identities. Okay, trigonometric identities. This is our beginning phase of these. We're going to add to these repeatedly, okay? And we'll do them all over and over again, repeatedly. These are pretty important things. They're coming up. I think we've already had them some. They're coming up later. They're coming up in the next chapter. They're coming up over and over and over again. Anytime it's repeated like this, you know it's got to be fairly important. So in trigonometry, a great deal of time is spent studying the relationship between these trigonometric functions. And in other words, what expressions are identically the same. Now, this breaks it into 3 classifications. You may have a few others later, but these are the major ones. The first is called the reciprocal relationship, which we've already been doing with our reciprocal key, our 1 over key, those kinds of things. The sine is 1 over cosecant, as the cosecant is 1 over sine, the cosine is 1 over secant is 1 over cosine, and tangent is 1 over cosine, and cosine is 1 over tangent. Okay. So those are your reciprocal identities. Get to know them. They're very handy. We've already been talking about them. Now, these are called the quotient identities. In other texts and other contexts, I call them ratio identities. The tangent is the ratio of sine to cosine, or the quotient of sine to cosine, which then, of course, makes the cosine the reciprocal of sine, which is, the cotangent reciprocal of tangent, which is cosine of sine. Tangent, sine of cosine, cotangent has to be cosine of sine. Now, these are just a little more complicated, but man, do they ever come in handy repeatedly. And the most popular one of these is the Pythagorean identity sine squared plus cosine squared is equal to 1. But you don't have to take my word for it. Okay? Does anyone remember in right triangle terminology, what is a sine? What is a sine? Is what? Some old hint. Opposite over hypotenuse. That's the sine. We're going to square it. Okay? Plus, what's the cosine? Adjacent over hypotenuse, and we're going to square that. And supposedly this is equal to 1. Let's see if it is. What's opposite squared would be O squared over H squared plus A squared over H squared. Okay, right? Bless you. Man, I think you got me beat there. Okay. Yeah. All right. Now notice here, we have a least common denominator, H squared. So let's just add the numerators together. O squared plus A squared over H squared. But what is O squared plus H squared? A squared. Opposite squared over, plus the adjacent squared.
Oh, it's the other one is squared.
Which is the? hypotenuse squared. So this then is just simply the hypotenuse squared over hypotenuse squared, and guess what that is? 1. Always, 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 the sine squared of any angle, any angle plus the cosine squared of that same angle, gotta equal 1. That's the Pythagorean identity of the Pythagorean theorem. It's right there in the line. Okay? So it's always true. Okay? Now, I'm going to erase that chicken scratch for a minute. Okay? I'm going to add some new. So I'm going to start with that one, which we know is always true. Sine squared theta plus cosine squared theta is equal to 1. We know that's true, right? Always. Okay. Now I'm going to divide all three of these terms by the same value. I'm going to divide them by cosine squared. Right? Is that legal in most states? Okay. Of course, as long as cosine theta is not 0. Okay, we'll just assume that. What's sine squared theta over cosine squared theta? Tangent squared theta, isn't it? Okay, so this would be tangent squared theta. And what's cosine squared theta over cosine squared theta? 1. And what's 1 over cosine squared theta? Secant squared theta. Always, as long as those are all legal moves, and that's exactly what we got here. They just wrote the 1 in front of it. All right. So all you need to know is this one. You can easily get that. Or we will okay. This time, we're going to divide that one that we knew by sine squared theta. I was really lazy. Okay? And what's sine squared theta over sine squared theta? 1. What's cosine squared theta over sine squared theta? Cotangent squared theta. And what's 1 over sine squared? Cosecant squared theta. There's the next one. This time we wrote it in the same order. Okay? So there's that. Okay? Now, since these three are true, I'm going to throw a few more up here that are equally true, and the only reason I'm going to do them is just because you'll see them in other forms. How are we doing? Oh my goodness. How did you do that? You know, today I won't let you. There's no extra charge for going over. Okay. Just today only. Okay. Let's see, where were we? Let me mark the space. We're going to start next time at example 5. Okay? But let me give you a few homework examples to go with that. You can do any of the odds 5 through 9. They all three are at calcchat.com. 5's at calcview.com. You can do either 11 or 13. They're both at calcchat.com. You can do any of the odds 15 to 21. They're all at calcchat.com. And you can do any of the odds 23 through 27. All of them are at calcchat.com. 27's at calcview.com. You can do any of the odds 29 to 35. There's 2 parts each. They're all at calcchat.com. And let's hold off the rest of them until we get a few more things done. All right, good deal. All right, remember, sorry about this, no class on Thursday, but we will make it up Tuesday afternoon. We'll have a class at 9:30 in the morning, and then Tuesday afternoon at 3:45, right? Yeah. Okay. And then we'll move on from there. All right, good deal, folks. Great class.